So now let's start discussing about the setup of the connections in TCP. So TCP needs to set up the connection before sending data, and the connection is usually set up by two TCP entities, and the classical example that we refer to is that one entity is hosting the client application, the other one is hosting the server application. Actually, this is important because the behavior of TCP in the client and in the server is not exactly symmetrical. And it must be so because, as we have already said by talking about the application layer, the server has to be always listening for client requests, okay? While the client starts the session when it needs the information from the server. So in order to be listening for already received client requests, the server application has to open a socket on the server side. And this socket is called welcome socket, and is opened using passive open command. As you can see here, the first step of TCP connection opening is basically acted by the applications. So the applications have to ask the TCP layer, the operating system of the host, to prepare to open the sockets. And the server is the first one to open the socket. It is the welcome socket. And it is called, this instruction is called the passive open. This is an example of a service primitives we have already introduced by talking from the theoretical point of view about the relation between the layers. And in this case, the service primitives that are used to talk from that are used by the applications to talk with the TCP layer are the socket APIs, application programming interfaces, that in practice are a set of library functions available when you are writing the application. In each programming language, you have this set of library functions. And the passive open, for example, is a specific procedure that the application has to invoke. And usually, since the server is always on, it's a daemon that is the server process is always on the server machine. And the invocation of the passive open is done at the beginning, at the bootstrap of the server machine. So when the server machine is switched on, it starts the passive open. On the other side, the client application issued an active open to the operating system only when the client has to start the communication with the server. So it is explicitly asked, for example, by a human user who is using a browser. So when your client browser application wants to download a page, an HTTP page from the server, at that moment the application sends an active open instruction to the operating system. So this is basically the first step in order to open the communication. Obviously here, when the client application sends an active open to the operating system, it will have to identify the server application by specifying the IP address of the host, the server host, plus the port number, that is the well-known port of the server application. In HTTP case, it's a port number 8. Moreover, the TCP implementation extracts randomly, choose randomly a port number on the client side that will be the source port address in the TCP segments. Okay. And of course, when the TCP segment is sent to the application, to the server, the client is aware of its own IP address. So once once the applications issued the commands on the server side and on the client side, then the TCP layer starts the communication that is necessary to set up the connection. And in order to do this, the client application is the first to send the request for connection opening, has to send first a segment which contains no data, so it's just a signaling segment, and it has the flag scene that is set. In this segment there is no acknowledgement number because you have no meaning. In fact, the segment has the ACK flag that is set off. But there is a sequence number, and it's the sequence number that the client application selects as a starting sequence number for that specific session. Okay. This initial sequence number is extracted, chosen randomly. Okay. It's a random number that is chosen, and is the beginning of the number sequence that will be used by the session, by the TCP session from the client side towards the server side. Why we need to extract it in a random way? Because we have to avoid problems of duplication of sequence numbers with other connections. So there may be other connections that were activated between the same set of processes, so between the same client application and server application. So they in the segments they use the same port numbers and the same IP addresses. That connection may be closed, but some packets, some segment may be late, okay, or some acknowledgement from the server to the client may be late. So if you have a mismatching in or duplication in the sequence numbers, it's a potential cause of errors. So this is why the sequence number, the initial sequence number, is always extracted. In the past, it was generated according to the internal clock, but then they realized that this is unsafe because it's something that is predictable. Sorry, I forgot to switch off the phone. And therefore it is not used anymore. Okay. Now we use only this random extraction. So then what happens? The server replies back and it sends another segment that contains no data, but in this case we have the scene and the flag both set to on, and that is the confirmation that the request for a new connection has been received. In this case, in the packet that is coming back, there is a sequence number and an acknowledgement number. The sequence number is the beginning, the initial sequence number that will be used to number packets, segments that will go from the server to the client. Where the first sequence number, the previous one, will be used to number the segments that go from the client to the server. Okay. And then notice that this sequence number is 67803. In the returning packet, there is an acknowledgement number that is 67804. Okay. This is the acknowledgement of the previous message. The previous message contains no data, so actually the payload is contains 0 byte. But in order to make the acknowledgement meaningful, by convention, the TCP consider that the first segment, the SIM, contains a payload that is long, that is 1 byte long. Okay, it contains one fictitious byte of information. And therefore, the acknowledgement number acknowledges byte. The byte number 67803, and it says to the client, the server is expecting byte number 67804. Okay, so it's a valid acknowledgement number. The initial sequence number that is chosen by the server is chosen in the same way by extracting a random number. Okay. So once the client receives this second message, second segment, it replies with the final segment, which has the byte, the flag ACK set, and the flag SYN cleared, and it has the sequence number that is the next one, so 67804. And the acknowledgement number that in the same way acknowledges the initial sequence number that was chosen by the server. That you see here is 5608, so the acknowledgement number is 5609. Okay? I have received 5608 and I'm expecting 5609. This third message, this third segment, can already contain data. Okay, so the client can start sending data. Of course, the first byte of this data will have this number, and then it can send other data in the payload. And this is what we have already seen talking about the application layer. If you remember, when the HTTP application wants to send a request, there is first this what we call the TCP setup phase. That was the first the exchange of the first two segments, this one and this one. So this was with SYN. This was with SYN and ACK. And then there is the third message with ACK. And if you remember, here we could already send the GET. Okay. Because the third message can send data along with the confirmation. Once the third message has been sent by the client and received by the server, the two applications that order the opening of the socket are notified that the socket is open. And in practice, this means that the functions that they have called in order to open the connection are returning the application. So they return as a result that the connection is open. Okay. So unfortunately, we don't have time to do any socket programming, but it's an interesting field. And by writing client and server applications, you can immediately understand what all these rather theoretical and fuzzy words they mean. But if you go on the book on Kurose, there is an example. If you want, you can follow. So this is basically the summary. So you have the passive open first on the server side, then the active open, then the SYN message, SYN ACK, and then the final ACK. And since this procedure requires the exchange of 3 segments before the connection is confirmed to be open, it is called three-way handshaking. Okay. Then there is also the termination of the connection. So the TCP connection can be terminated in a correct way by an explicit request by the two hosts that are in communication. And actually the termination can be demanded by one of the two sides. It doesn't matter which one of the two. And the way in order to request the termination is to send a message, a segment with the fin flag that is set. Okay. For example, in this case, the client application requests the termination of the connection, so it sends a segment with the fin that is set. There is sequence number also in this last message. The message does not may contain also data. In this case, it doesn't contain any data. And then the client application knows that the connection has been closed when it receives an ACK from the other side. Okay. Since the TCP connection is bidirectional, when one of the two, for example, the client requests to close the connection is only closed in one direction. So in this case, after receiving ACK, the client application will not send data anymore on the connection because the connection is closed on that direction, from the client to the server. However, it's still open on the other side. So the server can send other data to the client application with no problem. So it can continue sending data. At a certain time, there is a request of connection termination also from the other side, from the server towards the client. And this is again done by setting the fin flag into a segment. And even if the connection is closed on the other side, the client application can send an ACK to the server. Actually, the client application can send ACKs also in this case when it receives normal data. It cannot send data anymore, but it can send ACKs to the received data. So when this final ACK is done on the other direction, sent on the other direction, the connection is closed on both sides. So this is the summary. This is the connection of one direction, and then the connection also, the closure of the connection in the other direction. There is another, this is the nice way to close the connection that is used when all the behavior of the system is normal. There is also another way of closing connections that is called the connection reset. Again, it is done by using the flag. So when the reset flag is set in a segment, the connection is immediately closed in both directions. Okay, and so this is an emergency connection shutdown, and one of the two can send this segment with reset flag that is set. The other one that receives reset closes the connection and also closes the connection on the other side. Questions? So now we can start talking about the flow control, error control, and congestion control, the three functions that are the main plus of the TCP protocol, and they are a little bit complicated to understand, so they're not very easy. They are both carried out end-to-end. This is very important to understand. First, the flow control implementation. So we have already introduced this concept in a general way. Here we see how it is exactly implemented in TCP. So the receiver concept is the same. The receiver can control the flow of the transmitter in order to match the rate of the transmitter, the capacity of the receive buffer to hold information. So basically to avoid that the receive buffer gets congested. So the receive buffer accumulates the bytes that are received from that are carried inside the segments, and the bytes remains in the receive buffer until the receive application starts reading them. Okay, so the buffer has a limited space. It is written by the network and it is read by the application, and so the application has to read data sufficiently fast so that the buffer get not congested. There is also a transmit buffer that is in the transmitter, and here this buffer holds the bytes that are waiting to be transmitted because of the window mechanism that controls the transmission. So on this side, on the transmitter side, the buffer is written by the application and is read and emptied by the network, and data leave the sender buffer when they are introduced into the segment, and the segment is sent to the receiver. As we have already said, numbering is by byte. So the sequence number is used to identify each byte in the flow from the source to the destination. There are two flows always active because the TCP connection is bidirectional. In these next slides, we only show the flow from A to B, otherwise it's a big mess. So here you have that A is sending data to B, and B is only sending the acknowledgements towards A. Okay? So we are visualizing the buffer of A as a sender buffer, and the buffer of B as a receive buffer. Obviously, A contains also a receive buffer, and B contains also a send buffer, but they are not displayed here because otherwise it's too complicated. Okay, so the flow control is based on the sliding window mechanism with the plus that the window is the window size is dynamically controlled by the receiver. Okay, so here you find you see in this small rectangles, the array of small rectangles. They represent the bytes that are produced by A, by the sender, and these bytes are stored in the transition buffer, and they go from 1, 2, 3, 4, and so on and so forth. And then in the receiver, you have the bytes that are stored in the receive buffer. The center window is the blue box that you see there, and it is a sliding window, so it has a certain size, and it is located, it starts at a certain sequence number and finish at another sequence number. What is the meaning of all the other symbols that you find there? Okay, so the bottom of the sender window is the first byte that has not been acted yet. So the first byte that has not been yet acknowledged, in this case, is byte number 4. Before, outside the transmission window, you have the last byte that has been already acknowledged. In this case, byte number 3. Then, if y is the bottom of the window, so in this case y is equal to 4, then the window, and if the window size is w, then on the top of the window, okay, so this is the bottom of the window, and this is y. On the top of the window, you find byte number 13 in this case, that is given by y plus w minus 1. Okay, w is the current size of the window, and y plus w minus 1 is the top of the window. What is the meaning of this number? This is the last byte that can be sent while waiting for a new ACK. Okay, so in this case, the last ACK that has been received was acknowledging byte number 3. Okay, and this is the last ACK that has been received here. You can see it in this message. You can see that acknowledgement number is equal to y, in this case is 4. The meaning is the sender received correctly until byte number 3, it is expecting byte number 4. Okay? So this is a message that is acknowledging bytes until number 3, and it is waiting for byte number 4. So the base of the window, the bottom of the window, y, is always set to the last value of an that has been received. Moreover, the current size of the window is set to the w parameter that has been sent in the last message that has been received. Okay. This is the receive window, w, and TCP makes the send window equal to the current value of the receive window, so equal to, in size, equal to w. Okay. So then there is another variable that is x. This is the last byte that has been sent. In fact, here you can see this message that represented here, and the last byte that has been sent in the message is x. This means that the last message that left the transmitter going to the receiver carried a sequence number equal to x minus capital L plus 1. What is capital L? Is the number of bytes transmitted within the last segment. Okay, for example, in this case, capital L equal to 5 means that only one segment was sent. In fact, that here you see that bytes 4, 5, 6, 7, and 8, all these bytes were put into this segment, and the first byte of the segment was byte number 4. Okay. In fact, this is 8 minus 5 is equal to 3 plus 1 is equal to 4. So the sequence number of the last segment that was sent was equal to 4. Questions about this? This is the picture of the focusing on the send window. So the receive window will be, in absence of errors and transfer delays, so in ideal conditions, moves in sync with the send window. B determines the parameter to write back to the sender, depending on the size of its resequencing buffer, and A adjusts the width of the send window according to the value received from B. Okay. Here you can see that the send window and the receive window are in sync. On the receive side, the dark blue rectangle is actually the receive window, and the other light blue rectangle represents the buffer on the receiver side. Here we represent only the buffer in the transmission window that holds packets that have been sent and are waiting to be hacked. What happens if there is an error? So if there is a timeout, TCP works in a similar way as go backend. So it means that all the packets that have been sent and are not hacked, when there is a timeout, has to be retransmitted. However, there is a retransmission buffer that is dedicated to the retransmissions. So the bytes that you see here are always copied into the retransmission buffer. When a segment is acknowledged, all the bytes that are contained in that segment that was sent are deleted from the retransmission buffer because they arrived correctly, so they don't have to be retransmitted. If there is a timeout expiration, then the content of the retransmission buffer is sent. So the operation of this transmission buffer is momentarily stopped, and the sender starts fishing out segments from the retransmission buffer. So this buffer during the retransmission continues. Now let's go on the senders on the receive side. Oops. I'm sorry, I missed my. This is on the right. There should be receive window. On the left, there should be send window. So we go to the receiver side, and let's look at this buffer. So you have the resequencing buffer, that is the light blue rectangle. Inside the resequencing buffer, there is the receive window, that is the dark blue rectangle. The sender buffer, the buffer, it has a fixed size because usually you have you don't change the size of the buffer during the connection, and it is always let's say a sliding device, because the first byte that you find inside the received buffer is the first byte that has been received correctly but has not been read by the application. Okay. Outside the buffer you have the last byte that was received correctly and also read by the application. As the application reads the bytes from the resequencing buffer, the sequencing buffers start sliding towards the right. Okay. Then inside the resequencing buffer, you have all the bytes that have been received, but not yet eaten or eliminated by the application. And here, for example, there is byte number 2 and byte number 3 that have been received correctly, and also byte number 3 is the last byte that has been received correctly and already acknowledged. Okay. In fact, the last message that was sent from B to A contains acknowledgement number equal to 4. That means I have received correctly until byte number 3. I'm waiting for byte number 4. So from byte number 4 to byte number 13 here, this is the receive window. And the receive window starts from the last byte that the first byte that is waited for, and stops to the last byte that can be stored even if they arrive out of sequence. Okay. Basically, the top of the receive window is the top of the resequencing buffer. The receive window, if the resequencing buffer is blocked and bytes starts arriving to the receiver, you can see that the receive window shrinks. So the W, that is the current size of the receive window, start decreasing as the bytes arrive, and it starts increasing again only when the application reads the bytes from the buffer, so eliminates the buffer. In TCP, there is a mechanism that is a mixture between go back N and something more, say, efficient than go back N. So even if the retransmission behaves like go back N, it is possible to store bytes even if they arrive out of sequence. So the bytes that arrive out of sequence are not deleted, are not refused, as in the go back N that we have seen before, but they can be kept into the buffer, into the resequencing buffer, provided that there is space in the resequencing buffer. So for example, if byte number 11 arrives, it can be stored. If byte number 15 arrives, it has to be rejected because it is out of the resequencing buffer. So here byte number 14 is the first byte that will be discarded if it arrives out of sequence. Okay. So this is the first, in this situation, picture represents the case in which this last packet, the segment, has been sent by A but not yet received by B. In fact, you see that here you have another set of bytes, in this case 5 bytes, and this packet is still in flight, so it is not yet received. Okay. Questions? So let's look at this example that is perhaps easier to understand than the description before. Clearly, the mechanism is very complicated. No? It's a feedback mechanism, so it's not easy to understand. So, but here, in this example, we are displaying what happens when we have a connection that is being set up. And this slide represents the receiver side. The next slide represents the sender side. Okay. So, in the initial condition on the receiver, we have the receiver window that is goes from byte 1101 to byte 1400. Okay. It has a size equal to 300 bytes, and since in this initial condition all the bytes that have been received were already taken by the application, so the last byte absorbed by the application is 1100, it means that the receive window in the initial conditions has the same size as the receive buffer. Okay, so the receive buffer has a size of 300. The receive window initially has the same size. So all the buffer is empty. The receive buffer is completely empty. Now, in the second picture, the sender sent a first segment to the receiver. And the first segment contains bytes from 1101 to 1200. So it contains 100 bytes. Now you see that these bytes are received correctly, so the segment is acknowledged back to the receiver, and they are not immediately read by the application. Okay, so they remain in the buffer, in the receive buffer, and as a consequence, the receive window starts shrinking. It was 300, now it's 200. As you can see, the buffer don't move. The size is always the same, and since the last byte absorbed by the application is always the same, the buffer is blocked in the same position. So here there is a second segment that has been received by the receiver. The second segment contains other 100 bytes. Again, the application is not reading these bytes, so these 200 bytes remains momentarily in the buffer. The receive window gets smaller again. Okay, now it's 100. At a certain point, the application reads all these bytes that are stored in the buffer, and therefore the buffer slides of many positions. Now the bottom of the buffer is locked at byte number 1301. The receive window is again coincident in size as the buffer, because the buffer is completely empty at this moment. Okay, so all these bytes are absorbed by the application. This is basically what happens on the receiver side. And now let's go to the sender side and see what is happening on the sender side. This is the initial transmission buffer that you have on the sender side. At the beginning is empty, and at the beginning the size of the transmission window is 300, because it's according to the last notification from the receiver. Okay. Now the sender starts sending the first segment. The first segment is taking 100 bytes. These bytes are produced by the application, and they are placed in the transmission buffer because they have been sent, but they are not yet acknowledged. Okay, so they remain in the transmission buffer. At a certain time, these bytes are acknowledged by the receiver, and in the acknowledged message there is ACK, the acknowledged number, that is 1201. It means I have received correctly until byte number 1200. I wait for byte number 1201. But at the same time, the indication of the send window is 200, because if you go back here, the receive window was 200. Okay. So now the sender has to match, to resize its sending window in order to match the receive window. So according to the value that has been received, 200. So now the send window gets smaller. In the meantime, the sender sends another segment. The segment contains bytes from 1201 to 1300. Okay, so basically the send window is smaller, but also the free space in the send window is also shrinked. Okay, these bytes are stored here because they have been sent, but the acknowledgement is not received yet, and this is the condition after sending the second segment. So if you go back here, then it happens that the application reads all the bytes out of the receiver, out of the receiver's buffer. So the receiver window returns 300 in size. So when the receiver sends the acknowledgement for the last segment that has been received, it also tells the sender that now the window size has to go back to 300. And so this is the new situation. All the bytes that have been sent are acknowledged. So bytes are acknowledged until byte number 1300. So they get out from the send buffer, and also the indication of the window that has been received is 300. So the send window can get large again to the value of 300. Okay, so this is the final situation. So this is, I think, the best way to understand this feedback mechanism that is often not very clear also when explained in many books, because there is sometimes a lot of confusion about the meaning of the receive window. So notice that the send window is, the size of the send window is corresponding to the yellow box. This arrow inside shows you the free portion of the send window, but it's not the send window. Okay, it's only the free portion of the send window. If the send window, this free portion of the send window arrive to 0, then the sender has to stop sending segments, okay? Because it means that, as we have already seen in the previous examples, that it is not allowed to send segments anymore. Then there are these other phenomena that you can read, but I would rather take them off from the things that you have to know, because otherwise it's too much. Basically, these are the tricks that the receiver or the sender can play with the size of the window in order to avoid the behaviors that are very, let's say, inefficient in terms of transmission rate. It's something that I have already anticipated before when I talk about the tricks that you can play with the window size by lying about the effective space that is available in the buffer. But we can skip them. We can also skip the push function. However, I want just to tell something. Push is a command that is basically sent by setting the flag into the flag of the in the headers of the in the header of the TCP segment, and when the receiver receives a segment with a push flag that is set, then it is the receiver urges the application to read, to empty the buffer. Okay. This is very useful, especially when you have an application from the client side that has to send a stream of information, and then it has to notify the server that the stream is over. So that is the last character of the stream, or the last piece of information in the stream. So the way to do this is to send the last data into a segment with a push flag set. So then the receiver application, in this case the server, knows that that is the end of the message, and so it urges the application level to read everything from the buffer. Again, it's something that you can just better appreciate if you do socket programming. Also, this is about the urgent, the use of the urgent flag. Again, you can skip this. Just to know that while push is actually used in practice, especially by the operating system, the urge is not used anymore. Okay, so basically it's obsolete. Okay, so this is about flow control, and so if you don't have questions, okay, we can skip to the error control. Obviously, we will also do some exercises about these things, so it will be clearer. So the error control, I've already mentioned that the error control mechanism that is used in the TCP is similar to go back N with the timeout. It is by this mechanism TCP can recover segments that have been lost. The main cause of the loss usually is overflow, often not created in the TCP layer actually, but in the IP layer, because TCP segments travels on IP packets, and IP packets are managed by the routers, and in some routers you may have congestion in some of the queues, and so this can create packet loss. The retransmission is similar to go back N. There are some differences. The timeout expires basically each time. The timeout is counted each time a segment is sent from the transmitter to the receiver. So as the transmitter sends a segment, it starts counting for the timeout. And when the timeout expires, the retransmission is only for the segment for which the timeout has expired. Obviously, this means that all the bytes that are contained in that segment are retransmitted. TCP can keep also out-of-sequence segments in the buffer. So if the timeout expires on a given segment, for example, segment is number 2, here is a byte, or the byte, but think about the group of bytes. Then the other bytes are maintained in the reconstruction buffer, provided that they don't overflow the reconstruction buffer. The expiration of the timeout generate retransmission of the segment with this VC. When the segment arrives, then the window can slide forward the first non-active segment, and a cumulative act is sent to acknowledge all the segments that were out of sequence. Okay, so in this case, the segments, the buffer slides on. Obviously, the size of the transmission window depends on the flow congestion control mechanism. So it's not static as in the cases of go back N that we have seen before, but is matching what the indications of the receiver Okay, so the go back n actually here has an n that is not a constant, but is a variable. So this is an example. In this case, there are no errors. And here the maximum segment size is set to 100 bytes. And the window is initially set to 4 maximum segment size. Usually the window is measured in bytes, okay? But especially in exercises, once you know the size of the maximum segment size, it's very useful to translate the window size from bytes to number of MSS, because then everything is quantized in terms of MSS. In this case, we assume that A has data to send to B, so this is the client, this is the server. The server replies only with ACKS, and each ACK takes 4 bytes, 6 bytes. So, again, you have in black the numbering of the flow related to the flow from the top to the bottom, from the client to the server. In red, numbering of the flow from the server to the client. Initially, the sequence number is set to 100, so it means that the first segment that is sent by the client towards the server starts with byte number 100, and since the maximum segment size here is 100 bytes, and we assume that all the segments have consumed all the maximum segment size, the first segment will contain bytes from 100 to 199. Okay. The second segment will contain bytes from 200 to 299. The first segment from 200 to 399. In fact, you see the sequence number in the first segment is 100, and the second is 200, and so on and so forth. The segment arrives the receiver. In the opposite flow, the acknowledgement number here is initialized to 406. The receiver generates the segment that contains only the ACK, so the sequence number is 406, because it means that the first byte that has been not yet received is the number 406. Acknowledgement number 200. 200 means that this guy here has received all the bytes from 100 to 199, and it is waiting for byte number 200. Okay. So this goes back. Since the window is 4 maximum segment size, the sender can start sending all the other segments before getting or waiting for the acknowledgements. Okay. And the window is has the right size so that the transmission can be continuous, because in the absence of error, the acknowledgement goes back to the sender. Okay. While the sender is still sending the packets that are allowed by the first window. So here the window is from 100 to 400 to 500 basically. Here, when the first acknowledged has been received, the window slides on, and so the sender can go on sending bytes, and basically transmission is continuous. Here instead you can see the transmission of the acknowledgements. Each acknowledgement contains 6 bytes, and so also the acknowledgement numbers on the other direction increases. So here it is 406, 412, and so on and so forth. Okay, this is quite simple. Now, what happens if we have an error sending the segments? So here again we have transmission of the first segments as before. The first segment is received correctly, so the first acknowledgement arrives here. In this case, this makes the transmission window to slide on by another position, and so the transmitter can send until the fifth segment because of the transmission window that is slide on. But the second segment that is transmitted gets lost. So the acknowledgement about this segment is not received. And here you can notice that basically in this case the acknowledgement is missing. The third segment is received correctly, and all the other segments are received correctly as well. But obviously, when the server sends back the acknowledgements, you can see that the acknowledgement number is blocked at 200. And this also makes the window blocked so that the sender cannot send any more than this last segment. Then at a certain point, the timeout expires on the segment, on the second segment, and the expiration of the timeout on the second segment generate the retransmission only on the second segment. So here the second segment is retransmitted, and so then we can imagine, here is not specified, but we can imagine that once the receiver gets this segment, then it will reply with a cumulative acknowledgement that acknowledges also all the other segments that have been received but are out of sequence. So they were not thrown away but kept in the buffer. This is a case where you have an error in the acknowledgements. So again, all the segments are transmitted correctly. The first ACK is received. This makes the window slides on, so the sender can send up to the segment number 5. Then it has to stop waiting for the acknowledgement of the second segment. Okay. This acknowledgement has been sent, but it has been lost while traveling. The next acknowledgement arrives since the meaning of the acknowledgement is cumulative. At that point, the server, the sender, can start transmitting the other segments, because the window is slides on until the position that is 400. Okay. So this acknowledgement went lost, but since all the other packets have been stored correctly, there is no consequence on the transmission. The only consequence is a momentarily halt in the transmission, in the activity of the transmitter. We will have a look at Wireshark, but maybe in the next lesson. Now I want to go on. So now there is a problem that is new compared to what we have seen before, the timeout management. So we have seen, while talking about ARQ in the general term, that the timeout has to be designed correctly, so that it is close to the minimum required by the ACK to return to the transmitter. If you do the timeout too short, then the mechanism does not work. If you do it too long, then the mechanism is inefficient in case of error. The problem is that in this case, we don't have a constant delay, because while when we apply RQ at the data link layer, we are measuring time in a point-to-point connection, so the delays are basically constant. Here we are acting end-to-end, and as I have explained times ago, from the source to the destination we have a full network. Okay, so a full network where packets, the IP packets that carries the segments, have to queue into queues or inside the routers, and so we cannot say in a precise way, in a deterministic way, what is the delay. So the round trip delay is changing, and the solution, in order to match the timeout to the correct time, is to continuously measure the round trip time. So the round trip time is estimated by the sender, even without any need of communicating with the receiver. And the best way to measure the round trip time is to send a segment, and then wait for the ACK and measure the interval between the time that the sender was sent and the time that the ACK returns in. Okay. So each time the transmitter sends a segment, it receives the ACK and it can measure the round trip time. However, this is a random variable, so it's really varying from time to time in a random way, and the oscillations are sometimes always quite relevant, maybe quite relevant. For example, here you can see the time that is measured packet by packet, considering when the packet is sent and when the ACK is received, end to end, and you can see that the variation is remarkable. Many seconds of the variation. So clearly, the system cannot continuously change the timeout. It would not make any sense. So when this round trip time is measured, there must be some filtering mechanism that allows to smooth the behavior of this random variable. So the round trip time estimation is based on a moving average mechanism. So basically the sequence of samples that the sender have in order to estimate the timeout is given by the continuous measurement of the delay between sending a segment and receiving an ACK. But the value that is used to dimension the timeout is actually a moving average that is calculated out of these samples. So this is the law to calculate the moving average. It is very simple. It is called Jacobson algorithm, and is expressed in an iterative way. So it's called smooth round trip time. So the smooth round trip time, that is the estimation of the round trip time, is given by the smooth round trip time that was estimated as in the previous interval, plus the last round trip time that has been measured in the last segment, and the sum is weighted by a weighting factor. this weighting factor alpha varies between 0 and 1. If alpha is small, then the smooth is very high, so the measurement is very smooth because notice high weight is given fast. If alpha is large, high weight is given the last measurement. So the estimation becomes more dynamic. Usually the typical value is 1/8, 0.125, which is quite small. This is the estimation of the average of the round trip time, the mean value of the round trip time. There is also the estimation of the standard deviation of the round trip time. The standard deviation of the round trip time is defined by the difference in module between the last value of the round trip time that is measured and the smooth round trip time estimation. Okay, the average value that we have defined before. And also in this case, the smooth standard deviation is defined by this expression. You take the smooth standard deviation value that was calculated in the past, in the previous step, and then you combine it with the last standard deviation that has been measured, and the sum is weighted by a weighting factor that usually is 3/4 and 1/4. Okay. So the smooth round trip time and the smooth standard deviation are used to dimension the timeout. The timeout is calculated as the sum of the smooth round trip time, is the average, plus 4 times the standard deviation. Also, this parameter 4 is can be adjusted, but 4 is the typical value. And this allows you to have a margin in the case of outliers in terms of round trip time, so momentarily increases of the round trip time. Since this is everything is defined in the iterative way, you have to specify the standard condition, the initial conditions, and usually the initial timeout is 1 second. Okay, so since it is late, we can stop here. Then we will go on with this part. So next week we have regular lessons. Then there will be, we will lose Wednesday, yeah, first Wednesday, but not Tuesday. Okay.